Welcome back, geometry friends. We're going to keep going on section 2.5 today. So we've gotten really the early start to writing proofs. We've gathered all of our weapons. By weapons, I mean all of the definitions and the properties and the postulates and the theorems. And now we can start to apply them as reasons in our steps for proofs. So this is section 2.5 continued. Here we go. Are you ready? It's our first official proof. Dun, dun, dun. Here we go. All right, well, first of all, let's just look at this. This is what a proof generally looks like, folks. You're given a given. That's all the information that's given to you. And it's solid, like it's all true. There's nothing false here. Everything that's given to you is set in stone. Your job is right here on the proof. They're going to tell you, with all that given information, can you prove that? Okay, and that is your goal right now. A lot of times I'll have a diagram over here on the right hand side, but if not, then you should draw one based on the information that's given. But here are diagrams given to you. All right, well, let's just look at this. This is saying that given segment RT and segment PQ are intersecting at S. Okay, that looks right. So that RS, the length of RS equals the length of ST. Yeah, that kind of makes sense in the diagram if you look like it. And then the length of ST equals the length of SQ. Okay, now because we have a diagram, folks, we should always take our given information and mark our diagram with little congruent marks so that helps us see things. So I know that RS is equal to PS, or RS and ST, RS and PS are congruent, and then ST and SQ, which are two different sets, so I'm going to use two different little dash marks. All right, so that helps to see. Now we want to prove over here that RT is congruent to PQ. Well, let's just look at our picture. I mean, doesn't that kind of make sense a little bit? That if I take RS and ST, which is one dash and two dashes, isn't that going to be the same length as the PS and the SQ together? Because that's also one and two dashes. I think so too. So it makes sense. We just need to prove it. All right. Now, this is what we generally make when we make a proof. We make what's called a two-column proof, where one column on the left are all the statements. What do we want to say? The reasons go on the right-hand side. Those are the weapons. Why can we say this? Oh, because of the addition property, because of segment addition postulate, because of the vertical angle theorem. All those weapons, postulates, theorems, definitions, properties go into the right-hand column. We need to write our steps in the statements column on the left. All right. Step one in every proof is the easiest, because all you have to do is write down the given. Okay, every step, every first step in a proof is always the given. So I'm going to literally write down, here we go, RS. Now I can write down the entire words if I want, but the most important part to pick out is the fact that RS equals PS and ST equals SQ. Okay, statement number one in almost every single proof I've seen is always just restate the given. Good, because that's where we want to start. We need a place to start. Now, what's the reason? Like, why do we have that? Well, because duh, it was given to us. So reason number one in almost every single proof is just the word given, because it's given to you. All right, there's our launching point. Now, we need to find a way to get all the way to here. How can we show that the entire length of RT and the entire length of PQ are equal to each other? Like I said, it makes sense. It looks like it's gonna be. We just need to show it by steps. Well, here's what I'm gonna do. I know if I add the RS and the ST, that should be the same thing as the PS and the SQ. So what I'm thinking is, I'm gonna go to my step one. Look at our step one on the proof. What if I take, since I have two equations that are equal to each other, can I just add the left sides and make that equal to the adding of the right sides? I think so. Watch this. I'm going to say that RS plus ST is equal to PS plus SQ. Now, in order to get there, I literally took the two equations I have here, 1, 2, and I just added them together. So what property do you think that is? That's the addition property. We basically just took two equations and we added the same thing to both sides. I'll put the addition prop. We don't have to say the additional property of equality. That's very official, but you don't have to say that. In fact, I'll just say prop for property. Okay, that sounds good. Well, again, I'm looking back at my goal up here. What am I trying to prove? That the whole RT is equal to the whole PQ. Well, don't you know, looking at step 2, don't you know that RS and ST, if I put that together, do you see what segment I made? Yeah, I made RT. And do you see how PS and SQ, if I add those together, I would get the entire PQ. So in a way, can you see, if I include the equal sign, that that's actually the proof right there? But okay, that's not enough to prove it, though. We have to actually show it in steps. But that's the general idea. So can we say, how about, let's take the left side. Let's say that RS plus ST, like we said, is equal to the whole RT. Well, why is that? How am I able to take two smaller segments and add it up to the longer segment? What's that called again? Ooh, that was a long time ago, wasn't it? When you add two segments and it was like a postulate? Ah, it was the segment addition postulate. So don't rely just on properties. Go back and remember all of your postulates and theorems because those will be used a lot in these proofs. So this would be the segment addition postulate that says two smaller pieces of a segment will add up to the larger segment. Now I'm going to do the same thing and say PS and SQ add up to make the longer segment of PQ. And since that's the same reason, since they both have segment addition postulate, I can put them both down in the same step. That is legal. If they have the same reason, then they can be listed twice under the same step in the statements. That's looking pretty good. I'm almost there. But now can you notice, I really want to show, I'm going back up to the top again here. I really want to show that RT equals PQ. Is there a way that I could show that RT in step 3 is equal to PQ? Well, look what we did. In step 2, I showed that RS plus ST was equal to PS plus SQ. Now I just said that, well, RS and ST, I can call that RT. And PS plus SQ, I can call that PQ. So wouldn't it be okay to just say that RT equals PQ? And it is, but do you know why? How did we get there? You see that if we look at step 2 here, we know that RS plus ST equals PS plus SQ. That was great, addition property. But remember, RS plus ST, by step 3, that's the same thing as RT. And PS plus SQ is the same thing as PQ. So can't you see that it's almost like I plugged RT in for RS plus ST, and I plugged PQ in for PS plus SQ. So when I'm plugging that in, I am substituting. So this is called the substitution property that we've seen before, but now used in real action here. And that's it. So basically I took a mixture of step 2 with step 3, and I got by substitution the final part that I want to prove. And I did it. Yay, check, we're all done. Good job, we proved it in 4 steps. So look at that one more time. Step 1 is always the given. And the reason is always given. And then what we did is we tried to add the two pieces to make them equal to each other by just addition. Oh, but what we said that each pair of pieces added to a larger piece. That was segment addition. And then I combined 2 and 3, and using the substitution property, I proved it. Hey, there's your first official proof, folks. Great job. Let's try another one. Okay, here's proof number 2. That was segments in proof number 1. This is going to be angles. Okay, we don't have a diagram, but I do remember what this one looked like. I think I had something like this. And something like this. And something like this. Okay, let's label some points here. And meanwhile, we can start making our 2 column proof down here. You can tell it's going to be a proof because you see up top, what do you see? The 2 magic words here, given, therefore, proof. That tells you it's going to be a proof. All right. So let me call this little guy over here angle 1. And maybe I can call the middle one angle 2. And this one's angle 3. And then maybe I can say that, excuse me, how about A is here, O is here, and C is over here. And then I can say that about B and D. All right, I think that looks good. All right, let's look at the given. The given says that the measure of angle AOC is equal to the measure of angle BOD, or AOC is congruent to angle BOD. All right, we'll just look at our picture. All right, that's kind of believable. Can we mark it? Always try to mark your diagram. So AOC, this whole angle there, is congruent to BOD, this whole angle here. Okay, that's fine. So if that's true, can we prove that the measure of angle 1 is equal to the measure of angle 3? Or that angle 1 is congruent to angle 3? We'll look at the picture. Again, I think that makes sense. If the whole AOC is equal to the whole BOD, I feel like 1 and 3 are congruent. It almost feels like I can get 1 and 3 to be congruent to each other by just sort of like taking away this middle angle. If I sort of take away angle 2, I'd be left with 1 and 3 being congruent. Okay, but again, I have to show that. So what's step 1? Always given. So all right, measure of angle AOC is equal to the measure of angle BOD. Reason, given. Always. Done. Okay. And we marked it in the diagram, and it looks very, very pretty. So now, how are we going to do this? When in doubt, just start using things that you see in the picture, whether you know it's going to be right, whether you know it's going to help you get towards the goal, anything you guys can notice. In the last proof, I noticed that 2 smaller segments added up to a bigger segment. That was cool. That was segment addition. So is there anything with angles that I could do? Like, can you see that the measure of angle 1 plus the measure of angle 2 add up to a bigger angle? Look at the picture. And which angle does measure of angle 1 plus the measure of angle 2 add up to? Can you see that equals the measure of angle AOC? Okay. Why? Why can I add 2 smaller angles and get a larger angle? It's the angle addition postulate. So again, don't forget these friends too. Okay. But can I do the same thing maybe with 2 and 3? So let me say if measure of angle 2 plus the measure of angle 3 adds up to a larger angle, and that would be angle BOD. Why? Oh, same reason. So I can put that under the same step number 2. All right, that's pretty cool. Well, what can I do with that? I do know in the given that AOC was equal to BOD. But look how I rewrote AOC. AOC is also 1 plus 2. And BOD is also 2 plus 3. So can I sort of combine 2 and 1 together? Watch what I can do. If AOC is equal to BOD, can I say that AOC, which is measure of angle 1 plus measure of angle 2, can I say that's equal to BOD? Because BOD was measure of angle 2 plus the measure of angle 3. Look what I did. I took statement 1, which said the 2 angles are congruent. In statement 2, I broke them down into smaller angles. And if the bigger ones are equal, do you agree that the smaller ones together are also equal? Because 1 plus 2 makes up AOC, and 2 plus 3 makes up BOD. So it's like I just took the 1 plus 2 and I plugged it in here, and I took the 2 plus 3 and I plugged it in here. Well, again, another word for plugging in. This was another case of substitution. Substitute, I can spell. Prop. Okay, so I substituted in. Ooh, we're so close. When in doubt, take a pause and look and see what we're trying to prove here. We're trying to prove that 1, look at our step 3, is equal to angle 3. I think that's right, but how can I get there based on what I have now in step 3? It doesn't look like I can do it really easy by just sort of taking away these angles here. Well, can I do that? Can I subtract both angles? Are they the same? Yeah, they're equal to the same. They're both the measure of angle 2. So can I sort of subtract them from both sides? If I do that, I would get the measure of angle 1 is equal to the measure of angle 3, and that's what I wanted. Now, but why? Why can I do that? Well, what did we do from step 3 to step 4? Do you see how I subtracted the same angle on both sides? So what property do you think that is? That is, yes indeed, the subtraction property. Let's look what we got. Did we prove what we needed? Yes, we did. And we just proved it. So there you go, folks. Those are two really good, just starting, beginning examples of how we do a proof in geometry. We always start with the given in the first step, and we just work our way logically, using things that we know, using weapons over here on the right side that we've used before and we know, and trying to get to the end. Sometimes there are many ways to solve a proof, and that's good. It's good to have multiple options. Our job is maybe try to find the faster way so we don't have to take too many steps to get there. But just the fact that you get there, super, super proud if you do. Because proofs are tricky. Now, I got a little question for you folks. There's two weapons that I want to talk about for a sec. Because these guys are actually really, really similar to each other. Our friend, the substitution, or our other friend, the transitive property. Because when you do that, they both sort of have the operation of plugging things in and replacing each other. So which one do I use with which one? Let me give you a couple examples here. Example number 1 here. If I say that AB equals CD, and then I say that that same CD also equals EF, then what can you say? Can you see that I can say that because AB equals CD and CD equals EF, I can just jump from here. I can say that AB equals EF. Now, what I did a couple things. First of all, this really is transitive. Because this is if 1 equals 2, but 2 also equals 3, then 1 equals 3. This is transitive property. Remember, transitive property came from the law of syllogism, right? So this is a really good example. If P then Q, and if Q then R, then if P then R. But could you say that because CD is also equal to EF, I'm literally going to plug EF here where I previously saw CD, so that I really have AB equals, not CD, but EF over here. So can that also be substitution? Yes, it can. So both answers work. It is a literal transitive property, A to B, B to C, therefore A to C. But it is sort of a version of substituting, so it is substitution. Okay, so we got both answers for that one. How about this example? How about if AB equals CD and CD equals EF, keep going, if EF equals GH and then GH equals JK, what can you say? Now, you could use substitution and work your way backwards, but probably the fastest way is to say, therefore, AB, since it equals all these are all combined, you can jump all the way in and say a huge syllogism of, therefore, AB equals JK. That also is basically transitive. Now, could you call it substitution? Yeah, you could, but that's really complicated because you have to keep substituting backwards and backwards and backwards. If we could do it in one step, it'd be transitive property. But could we do substitution? I mean, I guess we could. It just would be a lot harder. So I'm going to put subst because it is possible. But now here's the point, because I feel like I'm getting the same answer for both these examples. Okay, watch this. This one's important. What if AB plus BC plus CD equals AD? But I know off to the side that AB is the same thing as FG. And I know that CD is the same thing as RS. This is not transitive, because this is not if P then Q, if Q then R, if R then S. This is literally, I give you a very strong statement here, and I'm saying I can replace these now back into the equation. CD is the same thing as RS. So I can conclude that instead of AB, I can say FG plus BC plus, instead of CD, I can say RS equals AD. So what I did is I took AB out and plugged in FG. I took CD and plugged in RS. What's the reason for that? That is absolutely, no doubt, 100% substitution. Transitive? No, it is not transitive at all. So I'm going to put it down, I'm going to cross out. So it can't be transitive, it's only substitution. So what's the point, Mr. Brown? My point, friends, is that really, if you are not sure which one you are given, should you use substitution or should you use transitive? If you're not sure which one to use, when in doubt, believe it or not, transitive is a type of substitution, really. So the overall arching umbrella here of substitution covers everything. Transitive is sort of a version, believe it or not, of substitution. It's like syllogism, it's like substitution together, but overall, if you're not sure, when in doubt, just use substitution. Because substitution, if you notice in all these examples, substitution always worked. But transitive didn't always work. So again, my point is, in a proof, since substitution and transitive are very similar to each other, you're not sure which to use as your weapon, just go with substitution because it will always be true. All right, friends, there is the rest of section 2.5. As we keep going forward, we're going to learn more theorems and more definitions and more postulates, but we're always going to be including proofs there. So you were off to a great start. See you next time.